Okay, here we go. Focus. Speed. I am speed.
The Doppler effect was first described in 1842 by Austrian physicist Christian Doppler. Now, may we have our guest speaker, Dr. Genders.
Okay, so in this video, we are going to be talking about the Doppler effect. Now, most of you must have already heard the Doppler effect taking place in real life, like when a car passes by. You can hear the sound waves getting distorted as it moves along. So in this video, we are going to be exploring a bit of the mathematics behind this effect. So first we'll talk a little bit about what the Doppler effect is. And by definition, it is the change in observed frequency of a wave due to the relative motion of the source and the observer. Now, you must be wondering, what does this even mean? So I'm going to put a few pictures in the next few slides so you can better understand the idea behind it, because otherwise this is just a bunch of text. It is very difficult to understand. But basically, this is all the Doppler effect is. So if you can understand it, then we are done. The Doppler effect applies to all kinds of waves, including water, sound, and light waves. We will be focusing on sound waves in this project, but we will touch on the Doppler effect on light waves in the discussion of the relativistic Doppler effect. Oh no, relativity. Sounds scary, right? But don't worry, we'll keep it simple. Now, before we get into the scary maths, here's a qualitative explanation of the Doppler effect, which I'm sure you guys will like. As promised by our guest lecturer, we have a picture to illustrate the concept. As you can see in this picture, this ambulance is moving away from this guy. Let's call him A. And moving towards this other guy. Let's call him B. When the ambulance moves with a velocity v as such, the sound waves going towards A's ears get stretched out like this, leading to a lower frequency of sound being perceived by A. So let's say that FA is less than F0, where F0 is the frequency that is being emitted by the ambulance. Meanwhile, the sound waves going towards B get squished together like this. So we can say that the frequency perceived by B is more than F0. However, it is important and interesting to note that the frequency of sound emitted by the ambulance, which is F0, has not changed. The explanation I gave can be summarized in the table below. Right? Here's a little animation to further solidify your understanding.
We hence obtain the Doppler effect equation, where the frequency of the sound measured by the observer is equals to the velocity of the sound wave plus the relative velocity of the observer divided by velocity of the sound wave plus the relative velocity of the sound source. We tried to model a projectile motion by throwing a sound source and using the tracker software to plot the velocity time graph of it. However, we found that the path of the object does not follow the equations, and that is because the acceleration decreases with increasing velocity due to the presence of air resistance. If we simply have to model the equation to include the effect of air resistance, it is still doable. However, the sound source moves in both horizontal and vertical direction. It is thus difficult to model the relative velocity of the sound source with respect to the observer due to the two-dimensional calculations. But don't worry, we found a simpler way and more exciting way too. Here comes the next part of our experiment.
So let's get into a little bit of maths again. So like in our experiment, imagine a sound source that's spinning in a circle as shown. As we have learned before, the tangential velocity of the motion, v0, is just given by 2 pi r over t. So let's assume that our observer is standing in the y direction, down from the rotating source. So in this case, if you think about it, only the y component of the tangential velocity is actually meaningful for the Doppler effect. So remember the linear Doppler effect equation from earlier, which is this guy right here. So this is the exact same equation, except that we need the y component of the velocity of the source. After a bit of derivation, we get to these expressions below. So most importantly, we get the observed frequency in terms of time, which is this small t over here.
Now, we tie the sound source to the mobile phone at different radius of 0.8 meters, 0.6 meters, and 0.4 meters. The period of the revolution is 0.85 seconds as measured.
Okay. Oh my god.
We measured the frequency by putting the microphone directly below the fan. However, we realized that no Doppler effect is observed. Why is this so? When the source moves in a circle, the distance from the center is always constant and there is no relative velocity at all. Hence, we place the microphone a distance away from the fan, and this is the results we get. We analyzed the audio spectrum using Audacity and carried a Fourier transform to attain this graph. We then measured the highest and lowest frequency of each period and obtained the following table. The recorded frequency does show a periodic trend of 0.85 seconds each, which corresponds to the graph shown in the Demos calculator. Secondly, the amplitude of the frequency also corresponds to the theoretical model that we derived earlier. However, we can also tell that the recorded frequency tends to be lower than the theoretical frequency, and we postulate that the Fourier transformation took into account the background noises of lower frequency, leading to this inaccuracy. Hence, while our results may not be quantitatively accurate, we can see the qualitative patterns in our data that illustrates the Doppler effect. But where's the fun if we do not include light, which is more than half the topic of CY1308? The relativistic Doppler effect talks about electromagnetic waves, while the classical Doppler effect describes sound waves. What's so special about relativistic Doppler effect is that it includes the time dilation effect of special relativity, and it also do not involve the medium of propagation as a reference point, as electromagnetic waves do not have to travel through a medium. When the source is moving away from the observer, there is a redshifting effect. This means that the observed frequency is lower than the source. When the source is moving towards the observer, there is a blue shift effect, which means the observed frequency is higher than the source. But it's not all theoretical.
Frequency emitted by a deep sky object, DSO, are redshifted, and this is evidence for the Hubble law that the universe must be expanding. Secondly, calculating the velocity of blood flow in the veins and arteries using the Doppler effect to determine vascular issues such as stenosis. Thirdly, the Doppler effect enables the aircraft's ground speed and location to be determined based on analysis of frequency changes of emitted radar beams. Most importantly, the acoustic Doppler velocimeter emits ultrasonic acoustics to help calculate the Doppler shift in the wavelength of reflection from particles in motion with the flow.